So just as we discussed, so this and in fact it requires that. Mhm. Just one second. So let me just check that this is exactly what they have. Yeah, so this I think is what they have. Um, yeah, so this is yeah. So this is what they have in paper also. And then they so they write it, but then sort of more or less enforced that you must have these. If at all you're going to do a limit theorem with non-trivial things, if not things not going to zero or not, infinity, these concepts are already involved. Even at the one layer. So this means that so coming back here, it means that you can already say that is so. Since we're already at that. Okay, so now let's. I mean, so yeah. So then, so if there is, so then under those conditions, strong line is there, and you have. Uh, so so this so then the deterministic limit exists, right? And it is the expectation of any one of these things. So any one of these TIs, which is expectation of essentially Z1 times P of V times Z2, where Z1, Z2 and 0. So this already is saying something, right? So it's saying in the first layer, the that vector should have IID constant in the n01 coordinates, and then the second layer vector should have what? N1 by so like 1 by root 10 should be like a Z standard. Yeah, so V is 1 is 1. No, something is wrong. V is 1. Yeah, V is 1. So this is like the variance is like 1 minus square. Yeah, that's correct. Yeah, 1 minus square. That's so which means that it should be take a stand normal, you multiply by 1 over n. That's so already it is something say it's saying something because all like they look like the same length vectors. To get limits, get a limiting output, like the limit, so final output to be actually converted to constant. You need that first one has to be um, variance one, the second one has to be variance one of it is really teaching variance one over n square. But then it was it. Once that has happened, the limit is just the expectation of standard normal times phi times c. So for every e, so you know the final answer. But do we know the other things also. So let's just think, go back here. So with that, what can we say about this? H also is like the standard normal, scaled by Z, right? It's exactly it's scaling of U, and X is also like it's like that standard normal, and you apply your same function on each coordinate, so it becomes like it becomes it's again an ID, it's again an ID vector. Then on top of that, you multiply that like this ID vector, which was like some relationship function applied to a standard normal. If you take inner part of that with some normal vector, but the normal vector has each, so its coordinates are again ID, but each coordinate has variance 1 over and squared. And then once that has happened, once that has happened, you see that this thing is converging to a limit, which is constant.
But the package one could still imagine that maybe by using some other tool, one could even expand its space of even.
Yeah, so one thing you could try, the natural thing to do would be to do triangular arrays kind of thing. So, but I didn't do it. So, yes, you can do strong law. Yes, so because as you can see, right, this actually is like hidden in the notation of the strong law, but this is the usual notation, has usual way of spelling it, has this big limitation. The variables are not actually different. So you're taking a limit, but typically you have that like at least, and you have random variables also depend upon it, and then you're taking average of n on them, then again average of n on them, and so on. The usual statement does not handle this case, but there are similar handle this case. But the same proofs more or less give you that. So often the latest they go by triangular arrays. To prove that triangular array, you have like I at the nth level, you have n running. So under certain conditions, you can again get things. But yeah, but that so yes, I think some things they can handle. And yeah, so here. Okay, so up till this point, so this is the deterministic limit. This law, because it is a function of f, like in the end it's a function of f and y. Y is a deterministic. I mean, like, it's not random; it's given to you. It's a function of this thing and y. So so if the loss function is continuous and it has derivatives are continuous, then the loss function and its derivative with respect to in this notation that you're using, derivative of nodes and nodes, those also converge to deterministic limits. Just because the only thing that is random inside it also is converging to deterministic. Yeah. So all this, yeah, and then you worry about dimensions a little bit, and but that also we discuss last time. So that's fine. Okay, so then we started working on the equations for the gradient design for this. So the two parameters are u and v. So basically, to take the gradient of the loss with respect to u and the gradient of the loss with respect to v. And exclude the loss of the real number, then the gradient in the same space in your trying to. And the way the derivative is in the same space. Right? And then with that circuit picture, it becomes easier to visualize what kind of change does look like and why it's for that propagation. So we actually did this calculation last time. So in terms of these notations, with chi was, remember, the derivative of the loss of the function, f and h and x are already there. I think we can drop this one, etc. Only one layer. So then again, so we had this different learning rate kind of thing. And then it was that v. So v is equal. So I should put like time, right? So this. So this is at time 2, and this is at time 1, and this is at time 2, and this is at time 1. So this is time 1, time 1, time 1, time 1, time 1. So this is, of course, there's no time here. There's only time here. Yeah. So these are times. That's the time. So that's the gradient, right? So this dot basically says that these things depend upon the current parameters. So it depends upon z, it depends on no y, no y. Well, this one also depends upon y. These ones can't depend upon y. This one depends upon y, z, v, u. The others depend upon everything except y. V, z. Okay. And yeah, so V has this, V2 has this update, V1, U2 has this update. What we would want to say that these things are also converging to some limits. Okay, so that's what we want to say. That's what they want to say, right? So I want to say that these are. But this is maybe a little bit tricky, right? So why is it tricky? So can I even talk and then converting to limit? So what is the thing that goes with N? So T is fixed for the set loop or one. That any fixed T, if I am talking about Vt going to infinity, does that make sense? So Vt as something as n goes to infinity, the limit of Vt as n goes to infinity. Does that make sense? Just as stated. What's the dimension of Vt or infinity?
Yeah, so it's a matrix. It's an n-dimensional.
Yeah, ut is the n-dimensional vector, Vt is also n-dimensional vector, and n is going to infinity. So these are not even the same space. So what does it mean to talk about their limits? So at least nothing reasonable. It's not like you want them to be at least in the same metric space or something, or some like theoretical space or some metric space or some space element of. So that by itself does not make so much sense, right? So when they say that these things are converging to limits, what they would really want to say is something like this: that you take any coordinate, that is converging to a limit. And then the coordinates are somehow IID in the limit. So what does that mean? It means that as n goes to infinity, if I look at like any finite set, then they're independent, they're converging to independent. So these are the two things that so each vi is converging to some limit, each coordinate individually, and any finite set of coordinates will be independent. So that's the kind of statement you want to make. But is that okay? So forget about the independence thing for now. Let's look at even that one statement. Pi is convergent to limit. Like Vt, I, the I coordinate of Vt is convergent to limit. Does that also does that make sense? Or maybe it makes sense, but like would it give something interesting? Let's say you're talking about V1. We just have said what the distribution of V1 has to be. The normal, so the each entry is a standard normal with variance 1 by n square. 1 by n square. So what is it converting to? Zero. Yeah, zero. So that's not very interesting. So maybe it's better to talk about n times that. So that's why they have to do this. So you think of you basically whenever you're talking of these things limits, you try to take a limit of something that does not depend upon n as an n. So what does not depend upon n? So certainly for V1 it's n times C1, the distribution of that does not depend. The distribution of n depends upon. But U is not a problem. U is the n0. The U1 is not. But at least for V1, it seems like n times V1 is the thing to do. What it do is the thing is not depending upon. So yeah. So let's write that down. So and by the way, there are ways of making sense of this also in other context. But here I don't think there is like I mean, these kind of constructions actually abound a lot. Like if you take some finite things with like growing dimensions and take the limit of those objects. Brownian motion is the kind of use. But yeah, I constructed in this way. But yeah, but in this case, I don't think there is any. But I mean, there you usually have some other constraint on the whole thing. So in Brownian motion, for example, you're trying to extend everything to a. It's more like so you embed it in the same space in the end, which is like so you have basically so this is the Brownian motion is a good example. So there, what happens is that you have these fine functions, but what you have is these functions are defined on your finitely many points, and the number of finitely many points is increasing. But these are all points in the same space. So then you can just like sort of extend them linearly in each interval. So then they are all found in the same space, all connected from the same, and then you can talk about the limit. So, but yeah, here it's that kind of a thing. I mean, these coordinates you cannot sort of I mean, they're just different coordinates. There's no sort of. So there, the important thing is that these coordinates have a meaning, right? I mean, they're points on a line or something. Here, that's not there. I mean, let me just permute the coordinates. That should not change the output. So, yeah, so this is not meaning things. Even so, something like V1 and converge to 0 is not does not sound so interesting. V1 is even 0 entry wise. It does not look like an interesting statement. So what we have to do is some modified versions which do not depend upon ends. Then take their so what this means is something like NV1 is, for example. So this is so this seems like a natural thing to look at. The others are fine. So the variables that we are looking at are sorry, so variables we are looking at are u. So there's u, then there's x, and then there is f, and everything else sort of is not depending upon. So it's only v versus. Yeah. Yes. Let me just drop the superscript. So, I mean, anyway, there's only one layer, so the superscript was for layers. So in the time, so this x1 is x, the layer output x at time. So the dot is should product, and then yeah. So now let's think about it. So n times v1 was a standard normal vector. So we would want whatever is happening here to have one property. So like again, it should be like something with the cost. I mean, like its variance, its parameter should not depend upon n. So
variance should not depend.
yeah.
Yes, its variance should not depend.
Yes. So let's just see. So there are two sort of things going on. So let's just first just think in terms of variance of each entry. Variance of each entry should not depend upon n. So it should not be equal to 0 or infinity there. That x satisfies. Right? Because what was x? So h was just u times v, and x was the p applied and device to h. And phi is some fixed related one. So x has a property. And this z1, what about that? The z1 was the derivative of the loss. But the derivative of the loss depends only upon f. F itself was some constant, converting to a constant is not. So at least theoretically right now, it seems that all of this is like a constant. So
Covariance close to.
yeah, so that is an important thing. Let's think about it later. Yeah, so it's not quite right because these things are not independent. But whatever, let's not worry about that. Other than that, the entries. So this is some. So if you just think of converting, this is converting to some real number, fixed real number in pen. This is converging. This is not. This is just like it's an IID. Like each entry is an IID that variable which is not whose variance is not dependent upon it. Okay. So what should I put LV? 1. Yeah, LV should be 1. If LV is 1, then at least these distributions are changing in a way independent of it. Okay. What about this? So maybe let me write down the V thing first, whatever we discussed.
So the same argument and L should be 0.
Yeah, but let's just think about it. So, and there are parts of this argument about V that are not correct, right? So one of the that is the main, but we'll see how to justify that. So we would NV1 is N0y. So we would want the other term to also not vanish / blow up with n. So or more or less not depend upon n. So chi1 in the in limit has this property. Each entry which are IID, like the entries are IID, of x1 also has this property. So if we set second term also will be fine. And the question is so let's worry about that later. It's actually important. That's what causes all the trouble when you do go to two layers, two different layers. So yeah, the complicated stuff. Here it's not particularly important. The point is that so shifting to the simple scale is something that I look at say so I have this random variable. it's x1 to x, so that's same thing as FLN. So I have a random variable x1 to x, like this infinitely many random variables. And I look at the following. I look at x. Now I replace the ith step. I replace in the nth step. I replace each xi by xi times the average of the first step. And then more of the same thing will say that this also as n goes to infinity, some converges to IIT random variables. So more like xi times expectation. So that's the kind of thing that's used. But yeah, but yeah, it's a non-trivial thing. But the crucial thing is because it's only one number being multiplied to a vector, that's why it's working out. So something of that kind is okay. But let's do the same kind of heuristic argument for this for you. So now what? So this is as we argued some kind of a constant. Again, it depends upon this v extra. This is some kind of a constant. Right? And what?
V1 is like 1 over n, but you're adding on.
Yeah. So the whole thing. So it's like this v1 is like it has variance. No, v1 has a variance one. So entry of v1 have variance 1 over n squared. Okay. So
So if you add them up, you will get.
It is not add. It is not add. This is actually true product. Right? U is a vector, so it has to be a vector. So this is a vector. This is a vector. And you're multiplying it.
Okay.
Yeah. So now what should U be?
It should be minus.
So minus 1.
Minus.
L should be minus.
Yeah. So it should be like there should be n multiplying here, right?
Yeah.
Yeah. Similarly, you would want LU to be minus 1. The same argument, let's say. This is the same heuristic argument. So what was this? This n makes sense because as you said, right, NP1 is the correct thing. So it's like this n goes into yeah.
Why is phi dash? Phi dash is constant.
Sorry?
Phi dash. Yeah, phi dash is each one thing.
Yes, it should get to see. So what is H1? So H1 is U1 times epsilon, right? As D. U1 was N01. So each entry of each entry of H1 is like a standard normal, like scaled by Z. So Z is a constant, it's not changing with n, it's the input to the network. And then you're taking the derivative of P is a fixed function. So again, that's not changing. So it's an IID vector whose coordinates have distribution independent of n. Of side n. It's an IID vector of side n, which is coordinates of distribution independent of n. That you're taking the inner product, Schur product with this vector, which is also an IID vector entry, but with variance 1 over n squared. So this whole thing is an IID vector. at least in the first round, with variance that is of about one variance. It's not quite right, but yeah, again, same, but that's roughly. And then yeah, and then the another thing is not right is that you are multiplying it by something that depends upon all these things, but which is converging by limit nevertheless and goes to infinite. And you think, okay, that limit has converged, and then yeah, okay. So let me just check that I didn't do any mistakes, and this actually reproduces their stuff. Yeah, okay. Yeah, that's the. Yeah. So now what they want to say that after one step also, after one step of the forward path, things still roughly remain IID. Okay, so that's what you would want to claim. And why would that be the case?
We are seeing difference of two things.
Yeah, you're taking difference of two ID vectors. But yeah, so the thing is, why are they ID vectors? These are ID vectors by definition. Yeah, this these two. Here you have to argue. It's instrumental, but yeah, but that's fine. I mean, it can be done. So yes, so you have to argue that. So okay, so it's clear that this is the ID vector. This is also an ID vector. That is being multiplied by this x, other thing. That thing is a function of that ID vector, but it is converging actually with this ID vector. And but that thing is converging to a constant and then goes to infinity. So multiplying by that ring actually keeps that IIDness in the limit. So what does IIDness in the limit mean? It should mean something like that if you take any cylinder, extremely finite set, any arbitrary finite set, that in the limit is so then the cutoff is not a fixed set, and that the distribution of that is so that's what the whole thing. So if you look at the paper, they will write it now in terms of distribution. So so the point is that now because you're thinking of IIDK, you just say that each entry of this has some distribution, each entry of this has some distribution, etc. So that is called Z. So then this is saying that Z of NV, each entry of this is Z of NV1 minus eta times chi times Z of X. So that's one equation. The other equation for the distribution Z of M2 is Z of E1 minus eta times E Z times chi times again Z and E1 dot this. So this actually is this came from somewhere. This was the actual derivative of f with respect to h. So the derivative of f with respect to h also is an IID vector. That is what is being used. So because it's taking two IID vectors and taking the like two independent IID vectors. That is what two independent IID vectors and taking the and taking it to production. That's the inside. So let's just write this. And the thing to justify. Infinite. Infinite converges to. So that's I mean that's the interpretation of the theory. Yeah, and now you can start repeating this. So once you have that the limit I. So the same equation you now can try to do it at the next time, and the next time, and the next time, and the equations remain the same. And because with IIDness is remain the same. So okay. So for any fixed time t that is not dependent on that is constant, it's not dependent on n. You can keep doing that. Fixed t is important because because you really justify all limiting and you say take n large enough and everything is closed and so on. So all those errors can actually they're only accumulating constant number of times. Then by taking n large enough you can make it. So that's fine.
Does it show that as t increases you learn something?
No, so the usual thing you really fix the time t. Yeah, so this whole theory to like to fix the learning time t, and for that use that thing.
So you have some limit for Vt, then you look at the same limit for Vt plus 1. Is there
Yes.
an improvement? Let's say.
That okay. So that they don't talk about at all. So that's okay. The way they're supposed to apply this, they take your network. I mean, okay, so this is a special, but this thing applies to more than a network. Take this network. If you're seeing such a thing for a small value of n, then it should also happen for large values of n.
Oh, sorry. Okay.
So what they want to say that so you take your favorite network and you run it for some like you train it for some time for some large but not too large value of n with things scaled in the right way with what they are saying. So then you see some behavior maybe up till time t, the last one is you convert like improving and so on. What they would want to say that now if you increase n by a lot, you should see the same behavior provided you scale the. So what why is it useful? Because what it will do is it will take some small value, run all your sort of optimization experiment there to see what should I change, what should I make it be, what should this be that.
It's like basically scaling to larger.
Yes, yeah. And then once you are fixed with that, then the theorem hopefully is, I mean, okay, in the limit is saying that, okay, now if you just increase n by a lot, you should expect to see the same behavior.
So the question that went on is not why it learns, but rather if I learn something at a moderate scale, how do I scale it up to a large?
Yes, that is the goal of this meeting. It is not, yeah, it's not trying to explain why, yeah, it's not trying, yes, it's different from all the other things where you actually try to figure out what the limit is. That's not what it's trying to do. Trying to say whatever happens at some, I mean, there's a limit to the behavior, provided you scale things in a certain way. So when you go from small network to large network, so there's the ends, etc. Right? So how do you scale the entries? So now when the network becomes large, the initialization should be that the numbers actually is just something very small. So that is giving you this exact description. But then on the constant there, it's not telling you anything, like eta and so on. And those you try to optimize, yeah, or your network also try to optimize.
This was for one layer data.
So this is for one layer. Yeah. So now we try to see what goes along. So basically this issue it starts getting more hairy. Like this is dependent upon that.
And the non-linearities are differentiable, like
Yeah, that doesn't, but that usually is not the big issue. I mean, yeah. So the
It's just people usually smooth the non-linearity out. Like even in this paper, they do that. So they essentially value they use the smooth
yeah.
G and
Yeah. So yeah, I mean like the I mean yeah. So I guess the meaning one is that any liquid function is almost everywhere differentiable. That's all. So that is one thing. So that's the mathematical sense. So then it's as good as a differentiable function. But in terms of implementation thing, yeah. So in the yeah, for these things you like to make sure all the mathematics is fine. You replace it by GAD. But yeah, but yeah, it's I don't think that's a big deal for the practice. They probably run the same thing for ReLU also, and I would imagine it gives the same. Yeah, and probably the explanation is that essentially, I mean, there's only one point where it is going to call, and that point. So any more questions? Yes, let's try to do the second like two-layer kind of thing also. And see where. Yeah, I think I have some idea why things should break down. Let's just see if that works. Maybe today let me just write down this two-layer thing and like what the network looks like, and then you try to write down the equations.
and the amount of data.
No, any not amount of data. So yeah, so right now we are even think something much more simple. It's like we're doing SPD with batch type 1. So the data is just one. So this is actually a very simple one. There was just one real number. So the network input is one real number, network output is one real number. N is only the size of the width of the network. Okay, so that's the only thing that is changing. Yeah, so in this new P theory, that is the setup. Data is everything else remains fixed, only the width of the network is fixed. So let's look at the two-layer thing. Yeah, so let's look at a simple two-layer. So two-layer. So again, let's write it in our language. So there is a Z, and so the first step is U. I think that's what they call H, right? Yeah. So this is H. So H is just U times, you see. So let me write it here. So that is, sorry. So that is giving this. Then you apply phi entry wise, right? So that's called X. And then yeah, so this is the thing. So you yeah, so here is the yes, let me just follow their notation. So H bar. So H bar. So this is okay. So let me just see. So this is R to the N. Okay, this is R to the 1. This is just R. So this is also R to the N. This is also R to the N. This is a matrix. Okay. And this is, I think we are calling it H bar is equal to W times X. Okay. So this is in R to the N. And that's it, right? Yeah. And then you do again Y. Yeah, so let me give these names correctly. So this is called X. This note is called X. Yeah. So that's what it outputs. This is called X. They just call it X bar. So let me also call it X bar, which is just phi applied to this, and that's it. And then there's another one. And this is the node F, which takes two inputs. So one is V. V is as before R to the N. And this is R. Okay. So this is the value, and then of course there is a what is the notation I was using? That's the loss. So whatever the loss is. So loss is so whatever the output of the F node was and Y and okay. So yeah, so now so what the only the big change that happened is that now there is this W matrix. Which is converting one big vector to a vector. So far this will not happen. So yeah, so again let us yeah. So again, so we can try to do the same exercise again, which is so which are the parameters? What are the parameters? U, and W, and so again we'll have some initializations for those, and we'll try to figure out what's correct scaling, right? So again, let's say that U has. So I don't know if they take W to be symmetric, probably not. Yeah. So yeah, okay. So let's say yeah, so let's say that U again is So each of them has an entry filled in a particular column. So, yes, so again, so the network is specified, and what we want to do is again to write down the update equations. So what do we need to do to compute the update equations? And the gradient is equal to. Yes, we need to compute the gradient of what with respect to loss. Log with respect to V, log with respect to W, and log with respect to V. And we'll just stop there. And then. Yeah. So again, we'll use the same definition. So chi is the derivative of so chi is the derivative of the loss of vector there. Right. So that is so that of course depends upon everything. Like depends upon what are everything? C and Y. Yeah. So this one is the only thing that depends also upon Y. Everything else is not depend. Nothing else is depend upon. So as this is the same kind of thing as before. So this is the function of. Yeah. Okay, and so what we want to compute is the we want to compute this D loss, let's say with respect to V. Okay. So now I'm going to do this. We're doing the same as before. So exactly the same as before. So like same calculation. So D loss F composed with D. Sorry. Yeah. So because this like F cuts L from D, so that's the only thing. And yeah, so D loss F of V is this chi. Okay, so of course now it's going to linear operators and so on, right? But then later on we'll get some numerical numbers, numerical values. But right now let's actually think of the linear operator in the right space. And then what is DFV? So maybe let me write it as this. So this is like the DFV is how is that changing spectrum? So right, so it's an operator on this space, right? So it is right multiplication by x, and that's what it is. So yeah, but if you now we come back to model abstract world and write then just write x. It's good to keep the abstract in mind because it helps. It makes it actually is the correct answer, and then numerically. Okay, so this is fine. What about W? Probably what the mean W is similar to what can be do.
So D loss W. So again, you have to find cuts, right, in the graph.
So again, yeah, disconnects loss from W. So certainly that is correct.
So we can put D loss F. DF W.
Sorry, yeah. Now what?
The DFX times.
Yeah, so X disconnect that one, so DFX, then X W X.
Then
X disconnect the X bar.
X.
Yeah, so it's clear.
Because it's basically linear. So in this case, no surprises happen, right?
You just going on, it just looks at
The usual chain root. This whole circuit thing is more useful. I mean, even here, I think it's useful, but it's more indispensable when you have more complicated networks.
I think of it as linear operator in the line. So this is chi, what is df? So let's think of this. So df x bar. So f is v times x bar, right? That's what f is. So what is df? So it's the operator that acts by v. Yeah, so right, it's left multiplication by v. Yeah, so this is left multiplication by v.
So this I should think of as multiplication by chi.
Right. So derivative of a real number by a real number, it's the linear operator. It is multiplication by a number. Yeah. This is multiplication by chi.
This is left multiplication by v, or it's more like an inner product with v.
Yeah, because v is a vector.
But yeah, anyway, so left multiplication by v. Because you're thinking of v as a row vector, x bar column. And okay, now
So I have written down those two things. What about this x bar x bar?
Is entry wise multiplication by pi prime.
Yeah, it's it's
entry-wise multiplication by. So it's like really just
it's just pi prime of x bar. Pi prime comes to like apply entry wise on x bar. That's what it is.
so and then
It's like sure multiplication with that like of x bar. So
sure. With phi prime.
okay. Notice this.
That is just X.
So we should be
Right.
so So it should just be right multiplication by x.
Okay.
So now what is this? So it takes some matrix, so something in the space of W, like some quantity W. It first tries multiply the x, then should multiply with this, then left multiply, then it multiply, then the left multiplication will be yeah, and then does a multiplication by. So I should be able to think of it as a matrix also. So what is that matrix? So in there is a linear operator on W, right? It's linear operator in the space of W. So just take some delta W and convert it into something else in the same space. So it's a linear operator on that. It should look like yeah. So it should be, yeah. So some it might even be some larger thing. Might be four kind of. It might be a big matrix, but here I think it's not. So can we think of it as a matrix instead? So what it does in delta W is right multiplication by x. So I don't know the answer. So so you write first you write multiply by x. So let us see. So let us see what is the mapping, right? So this mapping is that delta W is being mapped to delta W x, right? Then should multiplication by so this vector, yeah, let me just call, yeah, okay. So let me just give this thing a name. Let me call this I don't know what is this. So let's call this S. Then it's a Schur multiplication. So delta W dot x times x is a, so delta W is a n cross n matrix, right? So that is a n cross n column vector. Then you're doing this like a just 1 second. Something is not right. Yeah, I should think of it as, yeah, so I should think of it as a matrix. Yeah, so it's and so what is that matrix? That's what I have to just figure out. So x then Schur multiplication by this. So this multiplied with S. Then there's an inner product with V. And finally, there's a multiplication by chi. So multiplication by chi would be fine. So I have to take a matrix. Right, multiplied by A. Then so going to be the so right multiplied by x. Transpose. Let's okay. Yeah, so okay, so what is the matrix? Yeah, right, now I have the answer. Now I can ask. Triangle matrix, I'll tell you. So let's just think, right? Why should you just times
B should have the S.
So why should you just make so basically what is the difference? It's a linear operator on the so it's not even linear operator, it's like a linear form. It has to map it to the same. So because we are not dealing with finite dimension space, it must be just inner product by some vector.
Yeah.
In the same space. So inner product with the same, so it must really be some other matrix that you are doing a entry-wise thing. Right?
So this matrix is X times B Schur product with S.
Yeah, that's it. So basically, the point is that yeah, so let me just write it. So V is actually a I'll just do it. So what is happening here? So where you take the Schur product doesn't really matter. But let's forget about the S and chi for now. Let's just look at X and V. That is the crucial thing. So this is the final thing. So this is what is mapping to. So this is what is this? So this is like there's W here, X here, V here. But V has been, let's say, one of V or X, it doesn't matter which one, has been no, I think it's fine. Yeah, V with this. So V dot S. But this is like so it's like a U transpose WV, but that is the same thing as trace of delta W UV transpose.
So matrix is X V dot S. And that's a matrix. It's a column again. So this matrix is sorry. Okay. So one more is that. So let's do that and then. So this is a matrix that's clear. V is a column because V is a column row vector. That's the miniature writing experiment for you. Kind of number. The only thing not to be careful is X has to we should plot with V, not with S, not with X. That will be important. Yeah. Yeah. That's important. So I need to think of it like this then. But it's not a coincidence. This had to happen. There had to be a matrix because that's the abstract theory of circuits that tells us. It had to be a matrix. Question is what was the matrix? So now the final one more thing is left is the. So I'm doing all these like these ones sort of in detail because I at least find them confusing because in these derivatives there are so many things, and so in this sort of clarify what is going on. And in fact, this is what TensorFlow etc. would do, more or less exactly the same order automatically. So what is the remaining thing? U. Okay, so how about that? Missed. So U again, so I can do L, so F disconnects. So I can do F, then X disconnects F from that, so X, then X disconnects this edge, then X disconnects, then find the edge. So I can again like the same thing. So F, X bar, X bar, X edge. Okay, so many of these you already know, right? So these this and this we already know what the operators are. So only the final ones are left. So what is D H bar X? These three are left. Correct. So these three we already did what they mean. So mistakes. Right. Yeah. So what is DH bar X W? Yeah, so it's left multiplication by nothing. Left multiplication by nothing and DXH. It's show multiplication by prime. Yeah, multiplication by 5 prime of yes, right. That's
just to keep things clear. Yeah.
And should multiplication by number and that is dx. What is dhu?
Yeah, multiplication.
Multiplication.
So so let me just keep it. So let us give these things names. So let me call this S, this one T.
S.
Sorry? Yeah, S bar and S maybe. Yeah. That's the easier one. And this one is what is this? This is multiplication by. Okay, so now again, so let's see. So we again do the same trick. So delta U gets mapped to what? So it gets mapped to Z times delta U, then shoot product with S, then left multiplication by W. And then what? And then yeah, so this I want to think of this as a vector, right? So that's what W is. So what's the vector?
Once again, you can write as a trace of.
No, yeah, this time I think it's simpler. It maybe it's easier to think of diagonal matrices or something, I think. So this says that so D loss U is exactly, so these numbers, the multiplications just come out, everything is linear. So this chi xi V times diagonal of S bar times W times diagonal of S. I think that's
Yeah, again, last time it was because there was some right multiplication also.
yeah.
This time, we know that.
Yeah, everything on that. Yeah. So it's okay. Yeah. So let's stop here and that's so the thing is like when we start writing things, so this and the thing that we are able to or I was able to just more or less the habit that that there is chi thing which is actually coded, but it won't matter because it's a constant and it's multiplying to each variable separately. That kind of thing will start breaking because of matrix and and so that's what we want to see.
we have missed many classes because of holidays. So we wanted to have one extra class. So is this Saturday fine? It's open. Which is
Whatever time you like.
so now we can have a vote on that. If it's okay. Yeah. Okay. I think you're the only two registered. Sorry?
Yeah.
What time? 10? 10 something. Okay. 10 on Saturday. So I'll post, make a post. Okay. Yeah, sorry for going very slow on this. Partly, there are two reasons. One is that one is that I was from notice. And other is that I think it's good.